In the summer of 2025, a small team of scientists sat down with a piece of software, a set of NASA trajectory files, and an audacious idea. Somewhere out past the orbit of Mars, an ancient visitor from another star system was falling toward the sun. And sitting in orbit around Jupiter, almost forgotten, was a spacecraft that just might be able to reach out and touch it. This isn't a thought experiment or a screenwriter's pitch. It's a real proposal, published in a real peer-reviewed engineering journal, backed by real orbital mechanics, that asked a genuinely thrilling question. Could NASA's aging Juno spacecraft actually be redirected to intercept 3I Atlas, the third confirmed interstellar object ever detected, as it swept past Jupiter in March 2026? The answer that came back was more complicated, more dramatic, and ultimately more human than any fake headline could invent. This is the real story of that proposal, the obstacles that stood in its way, and what actually happened when the moment finally arrived. To understand why anyone would even consider this, you first need to understand just how rare 3I Atlas really is. Discovered on July 1st, 2025, it was only the third object ever confirmed to have originated outside our solar system, following Oumuamua in 2017 and Borisov in 2019. Objects like this arrive maybe once every few years. They move fast enough that our sun's gravity can never capture them, and once they leave, they're gone forever. There's no waiting for the next flyby, no second chance to send a mission. If you want to study one up close, you either happen to have something already in space that can reach it, or you miss your shot entirely. That's exactly the situation Harvard astrophysicist Avi Loeb, working alongside engineers Adam Hibbard and Adam Crowell from the Initiative for Interstellar Studies in London, found themselves staring at in mid-2025. Juno, for context, is NASA's Jupiter orbiter, launched in August 2011 and settled into orbit around the gas giant since July 2016. It was built to study Jupiter's atmosphere, its gravity field, its magnetic environment, and its poles, and by 2025 it had spent nearly a decade doing exactly that. But Juno had a problem. Its main engine had gone unusable back in 2016, not long after arrival, forcing the mission team to rely on smaller thrusters for any subsequent maneuvering. The spacecraft was also, by mid-2025, staring down a scheduled end-of-mission plunge into Jupiter's atmosphere, planned for around September of that year, largely because continued funding for an extended mission simply wasn't available. In other words, Juno was a spacecraft on borrowed time with a damaged engine about to be deliberately destroyed. And yet, buried in its orbital geometry, Loeb's team spotted something remarkable. Juno's highly eccentric orbit around Jupiter, with a low point of just 73,400 kilometers and a high point of roughly 5. 8 million kilometers meant the spacecraft was, in Hibbard's own words, teetering on the very brink of escaping Jupiter's gravity entirely. It would only take a relatively small nudge to break free. The team published their full analysis as a peer-reviewed paper in the journal Aerospace, using specialized trajectory optimization software called OITS, originally developed by Hibbard, combined with orbital simulation tools called Rebound and a numerical optimizer called Nomad. The results were striking in their precision. According to their calculations, 3I Atlas was projected to reach a distance of about 56 million kilometers from Jupiter on March 16, 2026, a distance that happens to sit almost exactly at the edge of Jupiter's gravitational sphere of influence, known as its Hill sphere. If Juno could apply a carefully timed engine burn sometime around September 2025, it could, in principle, be sent on a path to intercept 3I Atlas's trajectory directly. The numbers involved were remarkably specific. The team calculated that a maneuver called a Jupiter-Oberth maneuver, essentially a fuel-efficient technique where a spacecraft dips deep into a planet's gravity well before firing its engine, could bring Juno to intercept 3I Atlas using a total velocity change of about 6,755 kilometers per second, applied in 2 stages beginning around September 9th, 2025. That's a notably smaller fuel requirement than a more direct transfer, which would have needed something closer to 3 kilometers per second. Even more compelling, the team found that Juno didn't necessarily need to achieve a perfect zero-distance intercept to be scientifically useful. Using just a fraction of its remaining propellant, roughly 110 kilograms, only about 4% of what the spacecraft had left in its tanks, Juno could potentially close to within about 27 million kilometers of 3I Atlas by mid-March 2026, still close enough for its onboard instruments to gather genuinely valuable data. And Juno wasn't short on relevant instruments either. The spacecraft carries a near-infrared spectrometer, a magnetometer, a microwave radiometer, gravity science equipment, an energetic particle detector, a radio and plasma wave sensor, an ultraviolet spectrograph, and a visible light camera. Any single one of these, trained on an interstellar object from a fraction of the distance separating Earth's own telescopes from that same object, could return data no ground-based or Earth-orbiting instrument could ever match. This wasn't just an academic exercise floating around in a physics journal either. The proposal caught real political attention. On July 31st, 2025, U.S. Representative Anna Paulina Luna sent a formal letter to NASA's leadership, directly citing this research and urging the agency to seriously study how much usable propellant actually remained in Juno's tanks, specifically so that it could be repurposed for a 3I Atlas flyby. That's about as real and concrete as scientific advocacy gets outside the walls of a research institution. The research team also stated they were in direct communication with Scott Bolton, the actual principal investigator of the Juno mission at NASA, thanking him for his input as they refined their calculations. This was a legitimate, functioning collaboration between independent researchers and the space agency actually operating the spacecraft in question, not a rumor circulating on social media. But here's where the real story gets complicated and honestly, more interesting than a simple headline promising a guaranteed rendezvous. As Hibbard himself acknowledged plainly in his own writing about the project, there was a serious technical wrinkle standing in the way of a straightforward answer. Juno's orbital plane, described in orbital mechanics terms by something called its longitude of ascending node, turned out not to be well aligned for a mission to 3I Atlas. In plainer language, even though Juno was, in Hibbard's phrase, teetering on the edge of escaping Jupiter's pull with only a small nudge required, the specific direction that nudge needed to send Juno in wasn't a simple free lunch. The geometry mattered enormously, and it wasn't naturally in Juno's favor. Then there was the engine itself. Juno's main engine had not fired since 2016. The entire feasibility of this proposal hinged on a piece of hardware that had sat dormant, exposed to Jupiter's brutal radiation environment for nearly a decade, with its true operational condition known in full only to NASA's own engineering team. Hibbard was candid and appropriately humble about this uncertainty in his own public writing, stating outright that he was, in his words, merely a humble astrodynamicist, and that the actual decision about whether attempting this maneuver was practical rested with the key players on the NASA mission itself, who alone had the insider knowledge of the engine's true condition. So, what actually happened? As 2025 turned into 2026 and the critical Jupiter flyby date of March 16th approached, NASA never issued a public confirmation that it had executed the proposed engine burns to redirect Juno toward 3I Atlas. Reporting on the situation in the lead-up to the flyby noted plainly that even though some space observers speculated Juno's existing orbit might place it close enough to observe the object regardless, NASA kept largely quiet on whether the spacecraft had actually been repositioned for that specific purpose. In the aftermath, coverage of the event was fairly blunt about the outcome. Juno did not get a good look at 3I Atlas. The ambitious intercept, at least in the dramatic, close flyby form the original paper envisioned, does not appear to have been carried out. That might sound like an anticlimax, and if this were a fabricated story, that's exactly where a dishonest script would either invent a secret success or manufacture outrage over a cover-up. But the real ending here is more interesting than either of those because Juno wasn't actually humanity's only asset in the neighborhood, and the story of what we did learn from Jupiter's vicinity didn't stop with one spacecraft's limitations. The European Space Agency's JUICE spacecraft, launched back in April 2023 and bound for its own eventual arrival at Jupiter's icy moons in 2031, happened to be passing through the region at a genuinely useful moment. JUICE had already completed a gravity-assist flyby of Venus on August 31st, 2025, on its long, looping trajectory toward the outer solar system, and its imaging instrument, called Janus, was repurposed to capture a real photograph of 3I Atlas as the comet made its way through Jupiter's general vicinity in early March 2026. That image, released publicly, showed the comet's motion and its position relative to the Sun, marking a genuine, confirmed observation from a spacecraft that happened to be in the right place, even though its own scientific mission had nothing originally to do with interstellar objects. It's a reminder that even when one carefully engineered plan doesn't come together, the sheer number of active missions humanity now has scattered across the solar system means opportunistic science can still happen, almost by accident. It's worth pausing to actually understand the physics behind the maneuver being proposed, because the elegance of it is part of what makes this such a compelling real story. A Jupiter-Oberth maneuver works on a simple but counterintuitive principle. A rocket engine burn is far more effective in terms of the change in orbital energy it produces when it's fired at the point of highest speed in an orbit, which for an object circling a planet means the point of closest approach. By diving Juno down toward a very low altitude above Jupiter's clouds before firing its thrusters, the spacecraft could extract dramatically more benefit from the same amount of fuel than it would by firing that engine anywhere else along its path. The research team's calculations showed this two-stage approach, an initial burn followed by a second, smaller impulse near a point about 2. 68 Jupiter radii out could shave the total required velocity change down from roughly 3 kilometers per second for a simple direct transfer to just 2. 6.755 kilometers per second, a meaningful difference when every gram of remaining propellant matters for a spacecraft that had already spent most of its fuel budget getting to Jupiter in the first place and executing years of orbital adjustments once it arrived. The team also explored a more advanced version of the maneuver involving 2 separate thrust impulses rather than one, and their findings here were genuinely nuanced rather than a simple better is better conclusion. If Juno only had a small amount of propellant available, there was no meaningful benefit to splitting the burn into 2 parts. But if the spacecraft actually had more fuel in reserve than the minimum required, a 2-impulse approach could cut the necessary propellant mass by roughly half compared to a single burn, for missions aiming to close to within about 10 million kilometers of the comet. That kind of trade-off, weighing a more complex maneuver against a simpler one depending on an unknown quantity of remaining fuel, is exactly the sort of real engineering decision that never makes it into a fabricated clickbait script, precisely because it's genuinely technical and doesn't lend itself to a simple dramatic headline. It's also exactly why the researchers were so candid that the final call belonged to NASA's own mission engineers, who alone knew Juno's true remaining capability. It's also worth noting that Juno wasn't the first spacecraft anyone considered repurposing for an interstellar object flyby, and situating this proposal in that broader context helps explain why researchers were so eager to make it work. Years earlier, a separate research effort called Project Lyra, led by many of the same engineers involved in the Juno study, investigated whether any existing or near-future spacecraft could be sent to catch up with Oumuamua, the very first interstellar object ever detected back in 2017. Those studies, spanning years of continued analysis, generally concluded that catching Oumuamua would require propulsion technology considerably more advanced than anything currently flying, precisely because by the time an object like that is detected and confirmed, it's often already moving away from us too quickly for any realistic mission to catch up using existing chemical rockets. A separate feasibility study conducted specifically for 3I Atlas, examining whether a dedicated mission could be launched from Earth or from Mars to intercept it, reached a similarly sobering conclusion. Such a mission, launched from scratch after the object's discovery, simply wasn't feasible given how quickly 3I Atlas was moving and how little advance warning its discovery provided. That's precisely what made the Juno proposal so valuable in comparison. It didn't require building or launching anything new. It only required nudging a spacecraft that was already in space, already positioned relatively close to the target's path, using fuel that already existed in its tanks. Given how rare and fleeting these interstellar visits are, and how consistently every other proposed mission concept has run into the same brutal problem of insufficient advance notice, the Juno plan represented one of the only realistic windows humanity has ever had to actually reach out and touch material from outside our own solar system, using hardware already built and already in flight. That context also explains why NASA's Psyche spacecraft, itself en route to study a metal-rich asteroid in the asteroid belt, ended up making its own opportunistic observation of 3I Atlas around September 4th, 2025, passing within roughly 302 astronomical units of the comet during its own unrelated journey. Between Psyche's flyby, ES's JUICE capturing its own image near Jupiter, and the ground-based and space telescope campaigns running in parallel, the Juno proposal wasn't happening in isolation. It was one ambitious piece of a much larger, genuinely coordinated scientific effort across multiple space agencies and independent research teams, all racing against the same unforgiving deadline. A visitor from another star, passing through just once, that would be gone forever the moment it left. Meanwhile, the broader scientific effort to study 3I Atlas during this period was still producing genuinely remarkable results, entirely independent of whether Juno managed a close pass. As the comet made its closest approach to Jupiter on March 16, 2026, Avi Loeb published an extensive public accounting of what he described as 22 separate anomalies observed in the object's behavior since its discovery, ranging from its unusual sunward jet structure to its trajectory alignment with the plane of the planets. Around the same period, researchers using the ALMA radio observatory array reported record-high methanol levels in the comet's coma, while a separate team using James Webb's infrared spectrometer detected deuterium levels reported to be roughly 30 times higher than any previously measured comet, a finding that researchers connected to estimates that the object's ice may have formed something on the order of 10 billion years ago, potentially making 3I Atlas one of the oldest individual objects ever directly studied by human instruments. That deuterium measurement deserves a moment of its own explanation, because it's one of the more genuinely mind-bending real findings in this entire saga. Deuterium is a heavier form of hydrogen, and the ratio of deuterium to ordinary hydrogen, locked into a comet's ice, serves as a kind of chemical clock, reflecting the temperature and radiation conditions the ice formed under billions of years ago, before it was ever assembled into a solid body. A deuterium ratio 30 times higher than anything measured in a solar system comet suggests 3I Atlas's ice, assembled somewhere colder or under different conditions than anything native to our own sun's protoplanetary disk, reinforcing the idea that this object really did form around an entirely different and possibly far older star. It's the kind of measurement that decades from now, researchers may still be citing as some of the best direct evidence we've ever had about the chemistry of a planetary system other than our own, gathered without ever having sent a single spacecraft there ourselves. On top of all that, a coordinated search using 5 radio telescopes spread across 3 continents scanned 3I Atlas for any sign of artificial radio transmission sensitive enough to have detected something as faint as an ordinary smartphone signal strength coming from that distance. That search, like every serious search conducted so far, found nothing indicating artificial technology. But the fact that it was conducted at all, with that level of sensitivity, coordinated across multiple countries, is itself part of the real, substantiated story here. It represents, by some measures, one of the most sensitive searches for artificial signals ever conducted on any single object passing through our solar system, natural or otherwise, and it stands as a genuine technical answer to public speculation, rather than a dismissal of that speculation without evidence. Whatever else 3I Atlas turned out to be, it was subjected to more rigorous, more varied, and more sensitive scientific scrutiny than any interstellar visitor before it, using tools ranging from radio dishes listening for the faintest whisper of an artificial signal to infrared spectrometers, reading the chemical fingerprint of ice formed long before our own solar system existed. There's another layer of context worth understanding here, and it's about Juno itself, not just its proposed target. Juno launched from Cape Canaveral on August 5, 2011, atop an Atlas V rocket, and spent nearly 5 years traveling to Jupiter, including an Earth flyby in October 2013 that used our own planet's gravity to add speed to its trajectory, before finally settling into its polar orbit around Jupiter on July 4, 2016. In the years since, Juno completed far more science than its original mission plan called for, capturing detailed images of Jupiter's poles, its swirling storm systems, and close flybys of major moons including Io and Europa, all while its extended mission kept getting approved well beyond its initial end date. That's actually part of what makes the Juno proposal for 3I Atlas feel less like a long shot and more like a natural next chapter for a spacecraft that had already repeatedly outperformed expectations. Juno wasn't originally built with any interstellar object in mind, obviously. Nobody in 2011 could have anticipated that a visitor from another star system would arrive in 2025 at a moment when this particular spacecraft happened to be perfectly positioned nearby. But that's exactly the kind of fortunate accident that makes real science on occasion feel almost like fate. It's also worth understanding why researchers were so eager to get any spacecraft close to 3I Atlas in the first place, beyond the simple thrill of visiting an interstellar object. Every measurement we've ever taken of comets, asteroids, and other small bodies has come from objects that formed inside our own solar system, shaped by our own sun, our own protoplanetary disk, and roughly 4.5 billion years of shared history with everything else orbiting our star. An interstellar object is fundamentally different. It carries a physical, chemical record of conditions around another star entirely. Conditions no spacecraft built by humanity has ever sampled directly. A close flyby, even one that only gets a spacecraft to within a few tens of millions of kilometers rather than a perfect intercept, offers something no Earth-based or Earth-orbiting telescope can fully replicate. Direct measurement of the particle environment, the magnetic field interactions, and the fine structure of the object's outgassing gathered from vastly closer range and without the light travel time delays and atmospheric interference that limit every observation made from home. That's why a team of credentialed researchers was willing to spend months running detailed orbital mechanics calculations for a spacecraft with a decade-old engine problem and an uncertain fuel reserve. The potential scientific payoff, however uncertain the odds of pulling it off, was worth the attempt. So here's the honest, complete picture. A serious team of physicists and engineers identified a genuinely rare opportunity, ran the real orbital mechanics, published peer-reviewed calculations showing it was technically plausible, and got the attention of an actual member of Congress and NASA's own mission leadership. The obstacles that stood in the way weren't invented drama. They were real, specific, and technical. An engine that hadn't fired in almost a decade, an orbital plane that wasn't naturally aligned with the target, a mission already scheduled for termination due to funding constraints. And in the end, the most ambitious version of the plan doesn't appear to have been carried out, at least not in any form NASA has publicly confirmed. Juno, as far as the public record shows, did not get its close-up look. But the broader scientific effort around 3I Atlas continued regardless, drawing on Webb, ALMA, Hubble, ground-based telescopes, an opportunistic image from ESA's JUICE spacecraft, and a global radio search producing a genuinely rich body of new data about the object, even without the dramatic spacecraft rendezvous originally proposed. There's something worth sitting with in that outcome, beyond just the facts themselves. This story didn't need a secret confirmation or an invented collision to be worth 4,500 words of your attention. It's a story about how close humanity actually came to redirecting an aging, damaged spacecraft to touch something from another star system using nothing but existing hardware, careful mathematics, and a small amount of remaining fuel. It's a story about the very real gap between what's theoretically possible and what's practically achievable when the hardware in question hasn't been tested in years and the funding for extending its life simply isn't there. And it's a story about how, even when the most exciting version of a plan falls through, science doesn't stop, because there's always another instrument, another spacecraft, already in the neighborhood, another telescope somewhere on Earth still pointed at the sky, ready to catch whatever it can of something that will never pass this way again. If there's a lesson in all of this, it's that reality rarely hands us a clean, dramatic yes or no. It hands us partial answers, technical constraints nobody anticipated when the mission first launched back in 2011, and a scattered mix of successes and disappointments that, taken together, tell a far richer story than any single invented headline ever could. Juno may not have gotten its close encounter with 3I Atlas, but the attempt to make that happen, the real published mathematics behind it, and everything we learned about the comet through other instruments in the meantime, adds up to a genuinely compelling chapter in the ongoing story of how humanity is learning to notice and occasionally even reach toward the rare visitors passing through from other stars. And there will be a next one. Detection technology keeps improving every year, survey telescopes keep getting more sensitive, and the techniques developed here, the trajectory optimization, the rapid feasibility studies, the political and institutional coordination required to even consider repurposing an existing spacecraft on short notice, all of that groundwork now exists in a way it simply didn't before 3I Atlas arrived. The next interstellar object that enters our solar system may find humanity considerably more prepared to reach out and actually touch it, rather than simply watching it go. It's worth remembering, too, just how quickly all of this came together. From the moment 3I Atlas was first confirmed as an interstellar object on July 1st, 2025, to the publication of a detailed, peer-reviewed engineering analysis proposing a specific spacecraft intercept, only a matter of weeks passed. The initial preprint version of the Juno paper appeared on the Scriva repository by the end of July, underwent revisions through August and September as the researchers refined their calculations and incorporated updated tracking data, and was formally accepted for publication that same September, mere months after the object was first spotted. That's an extraordinarily fast turnaround for serious orbital mechanics research, and it reflects just how seriously the astronomy and aerospace engineering communities took this opportunity the moment it became clear what was actually out there. Whether or not NASA ultimately executed the maneuver, the fact that a complete, technically rigorous mission proposal could be conceived, calculated, peer-reviewed, and brought to the attention of Congress and NASA leadership within roughly 2 months of the object's discovery says something meaningful about how much faster and more coordinated planetary defense and opportunistic science has become compared to even a decade ago. In the end, whether or not Juno ever got its close look, this story was never about a single dramatic yes or no. It was about the very real, very human process of noticing an opportunity most people would never think to look for, doing the hard mathematics to see if it was possible, running into genuine obstacles nobody could wave away with enthusiasm alone, and continuing to gather what data could be gathered anyway, from whatever vantage points happened to be available. That's a far more honest and ultimately more satisfying story than any fabricated headline promising a guaranteed encounter ever could be. Sometimes the most compelling thing about real science is exactly how uncertain, how contingent, and how dependent on decade-old hardware and last-minute political letters it actually turns out to be.